a little different, but some of like the slides are the same, just the questions are different. So,
Okay.
yeah. Okay, so tutorial 9. I'll just pull up the chat in case somebody else comes. Okay. So yeah, the problem set 2 should have been graded. I don't know if you saw the grades yet, but they should be back soon. And November 24th is the last graded quiz. So in summary, this is sort of an extension from last week. This tutorial builds on what was discussed last tutorial. Emphasis is going to be placed on the quantum mechanical model and bonding, and we'll work on some examples for working with this quantum mechanical model. So the quantum mechanical model fixes problems faced with the Bohr model. Principal quantum number denotes the size of the electron orbit, and we use the letter n. It has an integer value beginning from 1. It can also be named by letters starting from k in capitals. The angular momentum quantum number describes the shape of the electron orbit, is denoted by L, can range from 0 to n minus 1, and typically you only encounter the S, P, D, and F angular momentum orbitals, and where S is equal to 0, P is 1, D is 2, and F is 3. The S subshell is sphere-like, the P subshell is a dumbbell shape, and most of the atoms in this course will only consist of S and P subshells. These are the ones used mostly in bonding. Note in the Bohr model, electron shells closest to the nucleus would have the highest energy value, but in the quantum model, this is not the case. First, sort of see that. And then the magnetic quantum number M denotes how each subshell can be orientated. Each unique orientation is called an orbital, and these can have values of minus L to L. Each orbital can contain 2 electrons of differing spin, and these spin quantum numbers reflect the different energy level of the 2 electrons within a specific orbital. And these are denoted with ms with plus or minus 1/2. And the filling of electrons can be sort of seen in this figure here, where we go from left to right in the periodic table and then up and down. So yeah, sort of from here, left to right, like that. Neutral carbon has 6 protons. So just a carbon example. In the nucleus with an atomic number of 6. Therefore, if we follow the table shown in the previous slide and fill each orbital with 2 electrons, we should get an electron configuration of 1s2, 2s2, 2p2. So let's see if I have a tree. So 1, 2, that's 1s2, and 2s2, and then 2p2. And in shorthand, we can use the noble gas notation, which we use helium and then 2f2, 2p2. And then the next example, titanium. If we follow the periodic table, the rules previously mentioned, we would expect calcium to have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. You can see that here. We got the 1s2, 2s2, 3s2, and we fill up all of the 3p. Then we go to 4s2 here. And when we get to titanium, one might write it out as this configuration here with 3d2, so it's here, where the d orbital comes from the 4p orbital. This is easier to visualize if you look at the periodic table. So I always like to just count the rows and then consider that this counts as number 3 here. And although titanium typically has a charge of 2+, so 2 of its 4s electrons get ionized, and its electron configuration would have the 3d2 at the end instead of the 4s2. And therefore, when we write this, we typically write the 4s2 at the end, just because those are the 2 that get ionized first. So some exceptions, a half-filled d orbital is favored. So atoms with 4 electrons or 9 electrons in their d orbitals will favor promoting an s electron into the d orbital to achieve a half-filled state. This is shown in chromium, where its configuration isn't 3d4-4s2, but rather 3d5-4s1, as its lower energy state is more stable. Then we have the octet rule. The noble gases have filled octets, and that's a filled outermost shell, meaning their electron configurations are very stable. This explains why they are very stable on their own and not reactive, as there's no room in their shell for bonding. And this rule is known as the octet rule. For example, if we look at neon, it has a filled 1s, a filled 2s, and then it has a filled 2p on its outer shell, and therefore it's stable. Bonding. So ionic bonding involves a transfer of electrons followed by a charge attraction between oppositely charged ions. So in the example of sodium chloride, sodium has an electron configuration of neon 3s1. Chlorine has an electron configuration of 3s2, 3p5. If we look at it, sodium would rather give away its 1 electron to achieve octet stability, while chlorine would rather receive 1 electron to achieve octet stability. Therefore, when sodium releases its electron, it becomes Na+, and when chlorine receives its electron, it becomes Cl-. And these form ionic bonds, which have a charge attraction between them, and that's shown in this figure. These solids do not conduct electricity due to this strong charge balance and strength of electrons to their nuclei. The charge attraction is general between all the ions, and the charge on an ion is not depleted by its participation in an ionic bond, therefore it is not directional. Covalent bonds involve the sharing of valence electrons between atoms. For example, we have here carbon has an electron configuration of 1s2, 2s2, 2p2. It's 4 electrons away from a stable octet. So it'd want to take hydrogen, which has an electron configuration of 1s1. There's 1 electron away from its stable octet. So if carbon can share electrons with 4 hydrogens, both compounds can have stable octets. And this sharing is known as a covalent bond. Covalent bonds can only occur between specific atoms. Other interactions can only occur as secondary intermolecular bonds. And covalent bonds can also occur between the same atoms. Carbon can covalently bond with carbon, and hydrogen with hydrogen, which can form hydrogen gas. And then the figure here shows how methane forms its octet stability, where this carbon shares an electron with each hydrogen. And these short straight lines represent a pair of shared electrons between atoms, and there is no electron transfer in this bond, which differs from ionic. Metallic bonding. Metals form a sea of electrons as seen in the figure. The valence electrons are not bound, but are allowed to move around freely. We also have band theory, which is covered, I think, this week. Since these valence electrons are free, it is easier for metals to conduct electricity. In other words, for electrons to flow through a metal, while the nuclei are bound to their lattice positions, which is sort of these positions of these dots here. The valence electrons form the sea of electrons, while the nucleus forms the ion core. And this also explains that the ductility of metals with high stress planes can shift past each other, since they are only held together by the sea of electrons. And I've shown in this figure how we can shift these atom positions easily with some high stress. Polymers do not tend to be conductive because they don't feature the sea of electrons. Instead, they have these tightly bound covalent bonds, making them in general insulating, but there are exceptions. As noted previously, polymers do not break their strong covalent bonds during plastic deformation. Instead, weaker secondary interactions are overcome as molecules slide past one another. And then for ceramics, for one plane to move past another, similar ions have to pass through an intermediate stage, leading to a fracture caused by repulsion. And that's shown in this figure here. where we have to line up the positive and positive, negative and negative atoms to sort of cause discharge repulsion, and that causes a fraction in our ceramic. Okay, so I sent out the practice quiz. I'll give you, let's see how long it is. It's 5 questions, so 8 minutes, 2 minutes per question, if that's okay.
Yeah, also another question about the exceptions for the electron configuration.
Yeah.
So in high school, I mean, my teacher, I'm not gonna lie, he wasn't the smartest guy, but
Yeah.
so he said that the exceptions that we would be kind of using in class would be chromium, copper, and molybdenum. Sometimes he said silver, but I was wondering for tungsten, seaborgium, gold, and like the other ones, are those
Mhm.
also exceptions or is that different? Because he never mentioned those ever.
Uh, like I think so. It's just the problem is that now
So many.
you have the F orbital sort of
Oh, I see.
also present, so I don't know, but I'm pretty sure it's just, yeah, again, you do have the, because like the
Yeah,
4F would be here, so
yeah. So tungsten and all that, I'm not tungsten. Yeah, yeah.
yeah,
Is that
tungsten, gold. I'm pretty sure they do still.
are exceptions? Okay. Or
Um, it's definitely something to look up, but I'm pretty sure it's the same rule applies. It's just now you have just
yeah, extra.
when
Yeah.
you, yeah, now you just have to consider that you have the F, so when you're writing it. But I'm pretty sure it still takes it from the S.
Okay.
Um, yeah.
I'm just curious. I haven't really read the top hats, I'll be honest, but
Hmm.
uh, would we be expected to explain like why there are exceptions and that type of thing, or is that beyond the scope?
I think you just really need to know that there are exceptions, and
Okay.
then like the only explanation you can really give is like that it's more stable, right? Like that's like the best, that's like all that was really taught, right? So
Okay.
um yeah, it's just being aware that there are exceptions, and then if you're asked about it, just sort of
Yeah.
saying like it's just a stability thing.
Okay.
um yeah, you weren't really shown like through diagrams or anything sort of how it gets that stability, but yeah. So that
Okay.
it might be explained a bit more later, but I don't think so. I think that's just like the most that you should know for now, and I think that's already for another course in the future.
Okay.
Yeah.
I'll do the quiz now.
Okay. Yeah. So let's say 33, 133.
Just curious, for when you guys say covalent and van der Waals or van der Waals and covalent, is it because you guys want to emphasize which one's more important or
Yeah.
okay. I don't really know if you want to wait, but I'm done, so we could still wait it out, I guess. But
Okay. Yeah, I'm just reading about so gold would be the exception. So
okay, but tungsten still.
I'm reading about tungsten.
Okay.
The exception with tungsten. I can send you this link apparently. Lanthanide contraction. So yeah, I'll send you this link. It has like a description, but it doesn't apply to tungsten because of that F orbital. But again, it's a little beyond the scope of the course, but there's like it's like a little paragraph here that sort of breaks it down. You want to take a look at that after. But yeah, gold would be the same. Okay, so here's the answers to the quiz. Any questions? I was going to talk a little bit about 5. Just because I mentioned earlier that polymers do have exceptions. This is something you might learn later on in the course. But a polymer has an alternating double and single bond, sort of like what a lot of these are all conductive polymers in the corner here. And or they have these conjugated structures, sort of what some of these have, that allow movements of electrons across the backbone. So when it has these sort of alternating double single bonds, you can sort of build a bridge across where you have these conjugated p orbitals being able to orient sort of across the backbone to form like this one-dimensional electronic band, and then these electrons can move across that single band. So whenever you see polymers sort of like this, where you have alternating structures, like also, I think if you like look at like polyethylene, you can make polyethylene in a certain way to also be conductive. So there are exceptions to it, but again, it has to have sort of like these types of structures for it to be conductive. So that's just like a cool little thing that you may learn later on, depending on which sort of field you go into. Do you have any other questions regarding
I think for the first one, I mean, I got the correct answer, but it was kind of more of a process of elimination. I'm
Yeah.
still like, I feel like I'm still, I mean, I feel like I kind of remember this from high school, but it's been like a year or so. I don't remember
For
too
sure.
much, but
Okay, let me just
why
pull
is
it up.
the 3D before the 4S again?
3D 4S 2. It's just because if you look sort of, you think about the shell, the 4S is going to be on the outermost. So if you like sort of drew like a Bohr-Rutherford diagram, like I know this is sort of different than Bohr-Rutherford, but
Mm.
um you literally drew like I can just draw it out right here. But let's say you had um that's our, what atom was it?
Vanadium.
Vanadium. So vanadium, like it's outermost, so you have like one, two, three, four. Its outermost would be those 4s2. That would, because it's on its fourth ring, right? So those are the first two to leave. So then the reason you put the 3D before that is because, again, it's from like the, when it will have a charge, those 4s are going to leave before the 3D, but technically the 3D have higher energy. That's why it's it comes after. You get what I mean?
Uh,
So
ish.
like the 4s is your most outermost, so it's your first ones to, let's say, leave, but your 3D have higher energy. That's why, like, let's say your metals will have the 3D, but your, like, the, like, calcium won't, right? um it also comes to like how these materials bond. So it's um like 3D is like just known as sort of like a metallic bond almost. Like there's no, like it sort of forms that sea of electrons. So like the best way to think of it is like your 3D are pretty stable when it comes to like staying with their nucleus. And then when you think of bonding, you only really want to think of bonding between atoms with their four, like with their s and p orbitals. So the best description I can give is that whenever you're dealing with a case like this, think of like if there is a d orbital or a s orbital and you're thinking of charge or something, it's always going to be the s orbital that leaves first. Is that like a useful
Uh,
answer at all? Or?
uh, I think my big issue was the fact that like if you draw the off-bar principle, like the arrow thing,
Mm-hmm.
the 4S comes first. So I was
Yeah. Um, no, this is like the best description I can give, but um, yeah, I know it gets confusing, but like like I'm trying to get at is that like, yeah, your S and P are gonna be your bonding and your first ones to sort of leave whenever you have some sort of, like, again, like when you do have a charge, that means that like those electrons have to go somewhere. So you're having some sort of type of like bonding in a way, right? So since your S and P are the ones that are always going to be sort of your bonding orbitals, just think of those ones are going to be the first ones to always leave, right? So your d orbitals, they're always going to sort of stay. That's what I'm trying to get at. So
okay. So if I were to kind of like remove oh wait, sorry, not one, sorry. I'm still trying to wrap my head around this.
mhm.
Can you go back to the answer? I don't remember. Can I see the answer again?
It was B.
Okay.
Yeah, B. again, like the best, like I know the 4s2, like that's what, like the diagram you were talking about, like the off-ball principle or whatever, like the D does have higher energy. That's sort of what I was trying to get at, but the S is on the outermost shell. So technically, like something has higher energy doesn't like necessarily mean that it's going to be the first to leave, right? So the best way I always envision it is with those Bohr Rutherford. Like I know it's not like exact, but those are the best ways to sort of envision what goes first, right? Isn't that?
Yeah, I'm like trying to Google it to see, and
Yeah.
I don't know. Google's giving me some contradicting answers. So
Yeah. Like for now, I think your best bet is just like sort of considering like this diagram that I drew here, like just if you try to envision it, but might be, again, just we write it that way purposely just because if you add charges after, like I guess we'll do some examples, but like when you do add charges to it, then you at least know that you're only, there's no, you can't really make a mistake, right? Because if you write it that way, then it's like, let's say you add a +1 charge or something, then you just have to remove one from your 4s, right? And then you don't have to worry about like technically writing it the other way is still right. It's just you might get confused later on when you start adding charges, right? Like I think it's just a matter of you write it specifically in that way to easily sort of work with it later on.
oh, I mean I'm looking through my high school notes right now, and I think I did have because I do remember this ish from last year, just not too much because chemistry. I mean,
Mm-hmm.
but I think I have a note to myself that says that because 3D and 4S are so close in energy, like the diagrams, that
Mm-hmm.
it doesn't matter too much. I don't know. I mean, my high school stuff is confusing me now, but
But that's what I was trying to get at, right? It's like
yeah,
it's a matter of you can write it the other way, but I think
yeah,
it's more of a formality to
hmm,
write it just in case if you start to add charges, right?
yeah. Okay,
Just
that makes sense.
because the S is gonna leave first, right? I think they just like the other way is still correct in a way, right? It's
Yeah, because in my high school notes, I have that for like copper 4S1 3D10 is like as correct as 3D10 4S1.
yeah,
So
yeah,
okay,
exactly. It's just
okay,
I think for this course, I would recommend writing it with the S on the end. Just
mhm.
again, it's like it's more of a formality thing, but it's the same. Yeah, it's the same thing. It's just a matter of again when you add charges and stuff. So,
Okay.
um, so here's the first sample problem. So we can just sort of go through it. So we have describe ionic, covalent, and metallic bonding, then give examples of each. So ionic happens through the transfer of electrons followed by charge attraction between oppositely charged ions. And then we saw that with our NaCl example. Na plus, we have an electron that leaves. Cl minus, we have the electron that comes in. And then that causes this sort of like attraction. Okay. And then covalent happens through the sharing of electrons between atoms, specifically a valence of electrons. So we could even just say like something like this. So these would be your sharing here. And so everything here has octet stability. And then metallic can be explained by two main models, the sea of electron model, where the valence electrons of metals are not bonded to a specific nucleus, but can move freely with while the nuclei have fixed positions, or the valence, or I think it was supposed to be electron band model, which is going to be covered this week, but I think in the textbook you already covered it, so we'll talk about it next week. Okay, so we're just gonna do some writing stuff, and then after we can go through, yeah, like the midterm and stuff. So so how would we start the first one?
I'd put neon in brackets, like any brackets, and then
Yeah,
I'd have 3s,
yeah,
and then 3p, and then like a 1 in superscript.
yeah.
Okay. For iron, I'd have argon in brackets. Argon. I'd have um I'd have 3D with 1, 2, 3, the 6,
Yeah.
and 4s2. Okay, for selenium, I'm trying to look for on the period. Okay, I'd have argon in brackets again. I'd have 3D10, 4s2, and then 4p4.
Yeah.
For copper, I'd have argon in brackets again. 6, 7, 8. Copper's an exception, was it? No.
Yeah.
Yes, it was. Do I remember?
Or what? Yeah.
Well, no, it was. I think because it's the charging, it's not anymore. 1, 2, 3. I 3D7, 4s2. I don't remember if the having like the what's it called again? Like being a cation would
So
make an exception.
yeah, it's still an exception, but you're still just removing 2 electrons, right? So even if you have 3D10 4s1, right? Still just minusing 1 off of here and then 1 off of here, right? So you just get 3D9. Yeah, regardless if you put it like 3D9 4s2 or 3D10 4s1, you still just would get the same answer if you just minus 2 electrons off, right?
Okay.
So yeah, the exceptions don't really, like, you don't have to worry about it when sort of minusing or adding electrons.
So if it was like copper 2 plus, would it still be like, sorry, copper 1 plus? Which one would I steal it from? Oh,
I don't even think it's a good question. I think it would be, well, let's see. I think it would, you'd take off the S.
off the S.
Yeah, I'm just gonna search it up quickly, but
Yeah, we just Google it.
Yeah, you take off the S. Yeah. So it's going back to like that, like what I was trying to say earlier. That
Okay.
the S is your bonding, your D is more stable. So yeah,
Okay.
so you'd get 3D10 on the end for copper 1 plus. Yeah. This would be that, okay? Titanium, what's titanium? 4 plus.
I think it's the same as Ari.
Yeah, it should just
Yeah.
argon, yeah.
Yeah. For
Cal-
calcium, let me find it. I can't find it on the.
Fourth row.
Oh, okay. Oh yeah, I see it. Just argon and then for S2.
Mhm. Phosphorus.
Neon and then 3 S2 and then 3P3.
Yeah.
Chlorine,
Chlorine.
neon again, and then 3S2, and then 3P5.
Yeah. And then argon.
Uh, I'd have neon and then 4S, oh, sorry, 3S2 and 3P6.
Mm-hmm. And then lithium plus.
I'd have 1S2
Would just be helium, yeah.
or yeah.
Yeah, same thing. Yeah.
I'm surprised I still remember this much from high school. Oh my god. So
You just like notice like phosphorus. If you ever work with phosphorus in the future, it likes to have, you just sort of look at its octet stability. It likes to have a 3+ charge. I think it also likes 5. I think those are like the main 2 charges. And then you can also have 3-. It's one of those funky ones where it can have plus or minus. So yeah, it's good to sort of, when you look at these things and you can want to achieve like octet stability with these types of things, you can literally just look at these configurations and you can sort of figure out charges from there.
I somehow remember something special about, I think, boron, but I don't remember what was special about it or something. There's something about it, I think. I don't remember from high school.
Boron, well, boron has a 3s2 and then a 3p or 2s2, 2p1, right?
It's just no, it's some there's something. I don't know if it has to do with electron configuration or something else. I might go back to my notes and look.
Mm-hmm. Let's see. Oh, boron tends to form compounds with 3 bonds. Is that what?
It could have been. I genuinely don't remember. I was wondering, could we practice with, I guess, the higher elements? Just because I think my teacher, when we asked to do that, he was kind of like, "Oh, don't worry about it." I
Yeah.
think something about the off-ball principle just breaks down. I don't remember what it was.
Um, well, do you want to try like one of the 4F ones? So like
Yeah,
lanthanum?
yeah, something like that. Just because
Yeah, we can.
I think once we got to like the G's, he'd be like, "Oh, don't
Yeah.
worry about it."
Yeah. And then you come to university and they tell you to worry about
Yeah.
it. Yeah, so let's try lanthanum.
Okay. Uh, yikes. Wait, let me draw the thing first. I might have to. Would it still be like xenon and then
Mhm.
6s2 and then 4f1?
Yeah, so let's I forget where the placement of the F goes, but F is stable, so I'm pretty sure it would go before the 5D and the 6S.
Yeah.
So
Yeah.
but if you look at periodic table, let me pull this up. So lanthanum's like a tricky one because it's actually sitting, like if you look at the screen right now,
Mm.
so you have 14 here, right?
Yeah.
But it's sitting right here. This is like its spot right here.
Yeah.
So it's actually a 4F0, I'm pretty sure. And then
Oh.
a 5, like it starts on this D position here. So it's like it's a 5D1 6S2. So
Oh.
it
Oh.
physically holds this position here. And
Okay.
it's the same with this one here, the AC actinum or something. So it's physically right there.
Okay. That's interesting.
Yeah. So even though it's one of the 14, like the 1F starts, or the 4F1 starts with cerium.
Okay. And if I want to take something like Oganesson, like the biggest one, and if I let's say like I want to force some electrons onto it, would you start jumping onto like G or something or
Sorry, which one are we looking at?
Oganesson, like OG, like the biggest one?
Oh, G. Okay. And you added charge?
Yeah, like let's say you want to add electrons to it somehow.
Well,
Would
that one's on the end, so it's not gonna
yeah, it
have,
doesn't.
yeah.
I mean, you
But
can still
like,
force some on, can you not? Or will you just not take any?
well, these are all stable as they are, right?
Yeah,
Like
but
this whole row, like it's
like
very
hypothetically,
unlikely.
if like hypothetically, if I wanted to like force some electrons on
Well,
it.
like if we can just look at like the next one, right? Like,
Hmm.
or like the one before it, right? Like if you want to add charge, like I guarantee you this one has charge of some sort.
Hmm.
And then there's gonna be the p orbitals, I'm pretty sure, that are getting removed, right? Those electrons. So what's
Okay.
that? What's that last one called?
Okay. I think this is enough. I don't think he's gonna test us on like that deep. So
Yeah.
well, if he
Here.
does, it sucks.
I'm just gonna make another comment.
Okay.
So there's with the F ones, there's some interesting things. So GA, I think, no, not GA, that's gallium. GD here, and this one here.
Or exceptions or
Yeah, so they have something similar
with the
where, yeah, so they have four, you would think there'd be 4F, wait, 7, right? Or 8? Not, wait, 4F,
eight.
yeah,
Yeah.
8. But since 8 is not halfway, it's gonna promote 1 to its 5D. So you'd get 4F7, 5D1,
Okay.
6S2. And it's the same with this one here. And then it's the same with these last two. So you
Okay.
have 4F13, right? So
Hmm.
what it's gonna do is, no, 4F13 is fine. It's the very last one. You have um these two. And It's technically 4F. Like what? It's supposed to be, if you count it, it's like I know this one's 0, but there's 15 positions, so it's supposed to be 15, but it's going to be 4F 14, and it's going to promote its 15 to the D. So
Also, when you use 0, do you like kind of do it for like just to make it clear for me, or should we always be putting the 0?
for like this one here,
Yeah, like in general, because you use like 0, like for the
oh, if you need to write it, no, you don't.
yeah. Yeah,
Like
don't do that. Okay.
yeah, you don't need to write it. Like the actual thing for lanthanum is 5D16S2. Like you don't need to write it.
Okay.
Yeah.
Okay. Okay.
But that's like what it is. Like if you think about it. So um yeah, so those are just like the F exceptions. So that's another
Mhm.
thing to think about. I don't think you'd be testing on that, but just an interesting fact. Okay, I guess that's it for the tutorial stuff. I'm just gonna stop the recording.